Great. All right, and welcome back, everybody. We're going to start our final session of CIW. We have presentations and then our group discussion. And so we're starting off with the future of Google testing by Sushmita and Kondareddy. And then we'll have one more paper and our discussion. So take it away.
Okay. Hi, I'm Avi, and Sush is on the call.
Greetings.
We work at Google on the main sort of testing and CI infrastructure team, TAP. This presentation goes over how we're going through a major paradigm shift with how CI is done at Google, mostly for scalability reasons. So first thing, I'm going to give some background on Google's development environment before going into how CI currently works at Google. So first thing, for those who aren't familiar, Google has a monorepo consisting of a branchless sequence of commits. We call them changeless or CLs sometimes, so I'll try to stick to commit, but if you hear me mess it up, then you know what I'm referring to. Google uses a build system called Bazel that roughly tries to keep compilations hermetic. You can kind of conceptualize the development environment at a particular commit as a series of files related to various compilation and execution targets in a sort of dependency graph like this. So once we, for Google, builds usually resolve their dependencies at the same CL. There are no version dependencies at different commits. This allows us to have this concept of a target being affected by a change or by a set of files, with the idea that if any files are changed, the full transitive closure of targets that are touched by that file or potentially touched by that file would likely need to be run if you wanted to do comprehensive testing. And what we'll kind of go over later is how comprehensive testing like that is not always scalable. So now I'll try to give an overview of how CI at large works at Google. You can broadly think of it as being broken up into 3 stages. We have pre-submit testing before commits are submitted. You have post-submit testing that is done to create these sort of signals for these golden commits that are then used for candidate creation, for release candidate creation, which feeds into a release pipeline of various release stages, QA, prod, so on. So I'm going to go by this step by step, try to both motivate why our system is designed like this and explain. So feel free to ask any questions in the middle if you're confused. So beginning of the developer journey, a developer is coding, doing some local testing on their machine, going through code review, and then they'll try to submit code. And so pre-submit testing at this point is intended to gate submission. And because this is an iterative process, likely you don't want pre-submit testing to be take up too much time. So the goal here is efficiently and quickly submit the code to head. And so the way that pre-submit testing is done at Google, it's fast, but it doesn't do this comprehensive testing that I talked about before. It's not testing every task that's reachable from the code that you've changed. It actually runs tests and targets based off of configured directories, depending on who owns the code that's being changed. So actually, we don't only do this, like run all targets in this local scope. We have a bunch of other ways that we filter tests. So one is this build dependency analysis. So we filter out targets that are in the scope but aren't affected by the files changed. We do dynamic test filtering at pre-submit time. So we have a machine learning model that tries to find tasks that are unlikely to break. We filter tests that we already have results for at that snapshot, by identical snapshot. And we filter out tests that might already be failing at the base state of the repository. Finally, we'll get some test results. We actually have another system. Flakiness is a big problem at Google. We actually have a system for ignoring test results when we believe them to be flaky. Another sort of measure to keep developer toil down. Okay, so this, pre-submit testing leads into submission. A change is submitted, becoming a CL. This submission process is actually quite simple at Google. Commits are submitted one by one and using a simple text merge, test-based merge. We are actually not using any sort of submit queue. We're simply looking, is there no file overlap between people trying to submit commits around the same time? If there isn't, your CL goes through. Otherwise, you might have to resolve your merge conflict on the developer side. Yeah. So this system does leave the possibility for post-submit breakages. We're not doing comprehensive testing before submission, and the main motivation for this, or like, well, why do we do this, is just that Google can't scale with the number of changes and the number of tests that can be affected to do this sort of comprehensive testing at pre-submit time. Yeah. So yes. So we need to have pre-submit testing and also post-submit testing. So this gets into post-submit testing. We need to sort of safely release groups of commits to be released into QA or prod at some timely interval. Yeah. And so the first observation is, most release systems don't actually need to release, very frequently, maybe every few hours for some sort of QA or staging environment, and likely once a day or less for production environments. So we can actually batch testing instead of doing it at every commit. And also, what we've talked about before, this sort of build graph dependency analysis is fairly simple to do and can have huge savings by skipping tests that are not affected by our changes. So what Google does for post-submit testing is a sort of batch testing that does this sort of naive filtering. So in this graph, you see the sort of red dotted line commits. Those are the ones that we are doing post-submit testing at. We call them milestones on tap. And so, we're not running any tests in the chain, the commits in between. We're running tests at these commits, and these are being used to feed release signals. So where do we go from here? So post-submit testing is happening at these milestone commits. It's going to say there's a breakage in this test, or everything is green at the CL. This is used to create release signals for, your release encapsulates this set of targets or tests. If they're all green, you're okay to create a candidate. And then after candidate creation, the release process proceeds. So here, all of our post-submit testing is happening cleanly before the release progression, before candidate creation. And so this is a kind of diagram of what the release process looks like. Yeah, as you can see, it's a staggered release schedule with different timings for how often we do staging, QA, prod, promotions.
Okay, so now we're going to get to so everything Avi talked about is what Google's testing framework looks like now. But in the future, in a more resource constrained world with like the size of the depot increasing exponentially, we want to be at a point where we can run the most valuable tests at the most valuable time. But this term most valuable is kind of a big bucket because there's so many ways to measure value. And so on the right side, we're thinking about like the value of like sort of like an intrinsic value of the test's existence at all. Because in like an all-knowing world, we would be able to gauge this value and we could use that to decide test priority. Say if like a test is super sensitive to mutants being injected into like the system, then that's a good test. Or if this test guarantees feature coverage. Or if we know that, hey, this failure occurred in our system, say at production, and we can recognize that the fix that went in contains a test that guards against this sort of outage being able to happen in the future, that's super useful information. And we can use these things to measure against dimensions we care about. For example, what would happen if this fault went into production? Like, what would the dollar cost of that be to the business? And even if it's really high, what's the likelihood that this will happen? And if we knew this, we could decide, hey, this test is super valuable, so we should run it really often. Or this test value is actually negligible compared to the resource cost of this test. And so we can do something like quarantine this test. But we usually don't know. Like if you think about a fairly straightforward example, say the sorted set collection in Java, what would the cost to Google as a business be if, say, the set guarantee was violated or the sorting guarantee was violated? Because we can tell intrinsically that, oh yes, this is critical, but we don't really have a way to like measure this directly. But something we do have more insight into and control over is if we say, okay, let's assume as a baseline that all tests are important and valuable and worth running, then how can we tweak when we run these tests to give us the most benefit for the resources we spend on it? And that can be along dimensions like the fault finding ability. It's much cheaper to correct mistakes earlier in the development cycle rather than later. And we have information about some of these things. Next slide. So when we come to this time value of a test, given that we've decided that all tests should be run, we can just decide when we run which tests. We can think about how long we spend running a test, but also like when in the dev process, this specific test is most valuable to run. And so for the rest of this presentation, we'll just focus on this like one part of the subproblem of when in the dev process we run. So our goal in this future paradigm shift that we're having is that we improve signal for cost by optimizing test timing. Next slide. So we want to do this by essentially shifting left and shifting right. And by shifting left, we're saying any test that's like high signal, especially to developers, we want to do earlier in the pipeline so that devs have faster signals so that they can fix any breakages they cause in the depot. But we want to shift comprehensive testing of things that may not be directly related to like the devs like code changes, but are important to the health of the release later in the like release pipeline. And so if you go back to the slide that Avi showed you earlier, it's fairly obvious immediately that there's a lot of signal that tap as the CI system provides that essentially aren't used later in the pipeline. So if you look at 2 o'clock and then at 4 o'clock, all of those are signals that we provide that essentially aren't used at all. And even amongst things that are used early on in the release stage, mostly none of that is used for production because like say in our production systems, most things roll out like once a day into the wild. But we provide signal every hour on the health of the depot, but that's not really used anywhere. And so this gives us a big opportunity for savings. Next slide. And another way you can visualize that same graph is that every hour, every 2 hours, we give you deterministic signals saying everything is green or like it's red. And we can change how this signal is provided to developers by using the fact that, next slide, we actually have a huge class imbalance in the targets that break. And this is information we've collected historically over the last like several years, in that 90% of targets in our depot have never broken in post-submit testing. There's 8.5% of test targets that have ever broken. And this means that you usually don't need to run everything to gate even like release creation, like release candidate creation. Next slide. And so now that we have these milestones, we can shift that into like a more frequent but probabilistic signals because we have data on what targets have failed more often. And so we can just run tests on those targets much more frequently and use that to provide signal to devs and to the rest of the pipeline about the tentative health of the build. And so as we like move into this, we'll have occasional comprehensive cycles to make sure like all tests are really run and we have quality signals. But in general, we'll have more frequent and probabilistic signal given to devs and fewer comprehensive cycles. And this ends up saving a lot of resources for us. Next cycle, next slide. And so if you think of this as sort of, so on the left side, you have like the tap green, and we run this every hour. So you can think of this sort of as like the bucket of all tests that need to run to, which right now is what we need to qualify like the candidate that's created by release. And we run this every hour. But next slide. We can now move to where we run these tests more frequently, and we call this a greenish signal, which is like a probabilistic signal that release projects can use to trigger parts of their pipeline. And now say TAP provides this greenish signal. Next slide. Release doesn't actually have to wait for TAP to finish running all the tests because TAP can start, and then as it's executing, it can start to like emit this like confidence signal saying, oh, hey, I'm pretty sure that like you're good to go, so you can get started. And we guarantee that by the time you're done, you'll have all the signal you need to guarantee safety. And so we essentially smear the rest of the tests across the release pipeline. And next slide. And we essentially fill up this testing bucket so that we run a set of tests before each stage in the release pipeline, therefore like reducing our resource costs and shifting comprehensive testing right. Next slide. And so we still guarantee that by the time a commit or like a set of commits reaches production, all tests are run. It's just how often we run them and when we run them that we change. Next slide. And so this gives us benefits on both the dev side and the resource side as like the CI team as a whole, because devs get much faster signal, because earlier they'd have to wait an hour or 2 hours to know that, oh no, I broke the defocus. As long as they know, they were like writing code, their pre-submits passed, it went in, and then like an hour later they get an email saying you broke Google, and they'd be like, oh no, and go in and fix it. But the faster they get signal, the more likely they are to have context on the thing they were working on and be able to fix it sooner. But we get huge resource savings. So even from going from 1 hour to 4 hours in our comprehensive like milestone testing, we see about a 50% increase in how many, like in our resource savings. So this is the paradigm shift that we are entering at Google. So if you have questions, Avi and I are here to answer them.
Yeah, Stan.
All right, thank you for the presentation. I've got one question with regards to feedback loops that are created, because it seems that if you select only tests that tend to fail and then run only those tests, then they'll fail even more.
Yes. So yeah.
So what are the feedback loops, and then what do you do to mitigate this?
Sure. Yeah. So I guess one clarification here is like we're still doing comprehensive testing at some point, but our base level post-submit testing is now going to be this sort of only test the things that are likely to fail. So I mean, there's two feedback loops. One is we should be discovering many breakages faster, which is not a negative feedback loop for our training data. It makes it easier, in fact. And yeah, and we should still be covering the rest of the tests. It'll happen once a day or 2 times a day that we're getting that signal of what are the other things that are broken that we didn't cover. Yeah.
And do you use data from both steps?
Yeah. Any breakage that made it into some like past submission is going to be used use for the training model. But yeah,
But then there's that comprehensive step.
yes.
Yes, we have an online question from Martin. Martin, go ahead.
Thank you very much. So my question is, how do you select the exact set of test cases that is being executed in those yellow, more frequent buckets here? Is that done via machine learning or some other method?
Yes. It's a machine learning model.
Point your
Oh, yes.
microphone.
Okay. There we go.
You're on, it's right here.
Okay. And this
I can-
one.
Yeah.
Yeah. Okay. Yeah. Yes. We use a ML model. I think I mentioned before that we are already using an ML model in for pre-submit filtering. Our model for post-submit filtering is somewhat similar, except the circumstances are a little bit different, and we can use information from the submitted CL or commit metadata, that sort of thing. Yeah. So coarse grain ML.
Thank you very much.
Yes, go ahead.
Yeah, so one question I have is, what do you do for a new test? You basically just, when someone creates a new test, you have to evaluate how important these tests is with your submissions before you kind of.
No, the ML model is doing the inference live on these downstream characteristics of the test. So even if you have new tests that still have those characteristics, but you would have less information. Like one of the signals that we're using is the execution history in the past. How often has it failed in post-submit? And you wouldn't have that signal for a new test. So
Right. So if I write a new test that I think is super important, it might take a couple of time. It might take some time before the system recognizes that.
One thing you will have immediately though is you'll have your pre-submit testing.
Right.
So if you wrote a new test, if you think it's super important, you're probably going to double check that it executed it pre-submit, that like you're actually running it.
Right.
And so you will have that test execution history there.
And another thing is a lot of times like new tests or new targets are unlikely to be deep dependencies of other things in the code. So if you're thinking of the distribution of these post-submit breakages, they tend to be things that are further dependencies than like something close to whatever caused the breakage, because you would catch those in pre-submit time. You'd be running all the tests that are close to your code.
Right. Yeah. Okay. So I guess another follow-up question is, does this also mean that it takes longer for the downstream tests? Let's say you made a change somewhere up the repo and then really far downstream you broke something end of the day. Does that take longer to get to you now because you're running these tests fewer?
Yeah, I mean, you're running these smaller cycles. If you miss a breakage in all of these cycles, then you wouldn't get that signal that this actually did break until this later comprehensive. So that's the trade-off here is we're going for resource savings. We're trying to catch as many breakages as we can earlier, but the ones we miss, that's going to add developer toil. And it's the same phenomenon of, if we ran everything in pre-submit, we wouldn't even have this problem.
You have infinite resources.
Yeah,
exactly. Thank you.
Any more questions? Okay. One more. This will be our last question. Mark, go ahead.
Thank you. So when do you trigger these more frequent and less frequently running builds? Is that just periodically, or is it like also kind of intelligently scheduled?
Yeah, it is periodically. So I think we kind of brushed on this. The existing like comprehensive testing cycles, we're running them about once an hour. And the idea is in the future, like these smaller ones, it's the same thing. We're picking a commit every 15 minutes, 20 minutes, and then we're saying, okay, over the range since the last time we did this, what are the most likely to break tests, and we run those. So yeah.
If I can add one note, Martin, if you think of the energy grid, you have sort of a baseline load from people just doing things, and they have like these baseline power plants that just like nuclear plants that start to turn off and on. The post-submit testing is kind of like that. It's a baseline load. It uses approximately the same amount of resources all the time, and it's never sort of really changing how much load is being sent. What we're changing is how we're sending that load, if that makes sense. Because it's always
Yeah.
the sort of the amount of machine resources that we give you. So if you were thinking of optimizing this from like the previous talk from the EdgeFlow people, like this would be the place where you want like the AWS instances that you like are the dedicated instances that you prepay for the year, because you know that the load isn't going to change, versus the ones where you have your sort of spiky load based on what people are doing. Hopefully that maybe clarified a little bit.
Yeah, that makes sense. Thanks.
Okay. All right, and our next talk is, in fact, our final talk, I think, is by John Bell, representing a large slew of authors, presenting the effects of computational resources on latent tests. So take it away, John, and then we will break for like a few minutes before we start our panel discussion.
Awesome. Thanks for the introduction, Tim. So yes, before I get started, big thanks to the huge set of co-authors that have worked with me and this project over, I feel like we probably started, some folks were working on this like at least 5 years ago. I think all